Okay, so good afternoon, everyone. I'm going to be talking about multi-body dynamics on escalators because David and I are working at RATP, which is the public transportation operator of Paris. And RATP owns a fleet of more than 850 escalators and moving walks, and has in charge 80% of its maintenance. So the particularity of our fleet is that it is, first of all, quite diversified. We have we have 24 different models, but more importantly, it is quite old. Some of our escalators were installed 50 years ago, and the average service life of our models is 40 years. So to make our escalators last that long, we do mid-life refurbishment, where we replace components, among them the steps. And over the past decade, we have installed, instead of the steel steps, aluminum steps, which are way lighter. So what brings us here today? Over the past few years, we have had an increasing numbers of collision between steps and cone plates. For what we decided to launch a couple years ago, a research project. And one rumor that was going around was that the step that we install now, the aluminum steps, which are lighter, disturbs the dynamic behavior of the escalators and increase the risk for the steps to rise. So the idea was to assess the impact of the step weight on the dynamic behavior of a step band. So for this purpose, we created a multi-body dynamic model. And we realized that we were able to study much more parameters than just the step weight. And to use the conclusion to optimize our maintenance policies and design methods. So here is the model I've been talking about. We directly went for a computerized solution for two reasons. First of all, because we have tried in the past to install measuring systems on our escalators, and that didn't really work for us. The measurements were very imprecise. Whereas with a 3D model, you can have a better control of the system inputs. So that has less chance to happen. And the second reason was that it is cheaper and faster to create a 3D model like this than install measuring systems on several escalators. So this model was created using Adam's machinery, which allows the creation of chain-driven systems. And before we go on, I want to give you more details about this model. So it's composed of two independent step chain systems connected with each other by the use of two shafts. There's also two independent damping systems used as a tensioning station. And of course, 70 steps and their rollers and two rail assemblies. So that makes a total of more than 700 parts, moving parts, around 17,000 degrees of freedom, which is why it takes around 3 hours to compute the 26-second animation you just saw. Which represent half of a full rotation of the step band. So you may have noticed on the previous video green arrows. So these are distributed load applied on each steps in between the lower and the upper cone plate to simulate the passenger loading, unloading, and carry. So part of the study was dedicated to the model validation, where we compared the model outputs to the result of an analytical model. Then we decided to run a first set of experiments where we tried different parameters, see if they had an impact on the model and if there were any interaction between them. So no interaction were found during these experiments, but 5 parameters stood out. Among them, 3 maintenance parameters. The step chain rotational damping, which reflects the step chain lubrication efficiency, the rolling friction between the steps, between the rollers and the tracks, which depend on the rail lubrication, and finally, the tensioning station adjustment. There are also one design parameter, the step weight and design, which was what we originally wanted to study, and one environmental parameter, the number of passengers carried and their position on the steps. So after this, we decided to run a second set of experiments using these 5 parameters, but it's time to assess their impact on the dynamic of the system. Given the computation time, we decided to perform a design of experiments. And based on the previous results, and given that one of our parameters is nonlinear, the position of the passengers on the steps, it seemed more interesting to focus on the study of the linearity of the system rather than a high number of interactions between parameters. So we used the Taguchi methods to build our design table. And the Taguchi table we selected allowed the study of 5 parameters on 3 levels for the linearity, and also allowed the study of 4 interactions. So this table requires 27 simulation runs. At each of these runs, we recorded a certain number of output. We selected in accordance with what we wanted to study. So we focused on 3 different aspects. First of all, of course, the risk of collision between the steps and the complete, but also the engine power required to repair the system, and the step bend component fatigue. So for instance, to study the chain guide fatigue, we recorded the contact forces of the step chain on just the chain guides. So as you can imagine, a model like this has some limits. The biggest one is that to reduce the computation time, we had to guide the steps using the tracks. So the steps, of course, can roll. They can have lateral displacements, but they cannot rise. So to assess the impact of our parameters on the risk of collision, we had to record the contact forces between the rollers and the tracks to give us an idea of the probability for the steps to rise, which was the trickiest part of the study. So here you can see an example of output graph. The evolution of the step chain link tension from the lower to the upper complete. For each of these graphs, we selected one value to complete our result table. So in this case, it is the maximum value, but it could be the minimum, depending on the output, it could be the minimum, the maximum, or the mean value. And here is the result table 1. It's been fully completed. Actually, it's just part of the result table. But finally, we performed a Chisquared test to assess the impact of our parameters on each of our outputs. So the number of passengers carried has an overwhelming impact on all of our outputs. We decided not to take into consideration its impact on the risk of collision because it is obvious that the steps have more chances to rise when they're full of passengers. The position of the passengers on the steps does modify the force distribution within the steps, but doesn't impact the dynamic of the step bend. The second parameter is the friction, the step chain lubrication efficiency. So it impacts both the risk of collision between the steps and the complete and the step bend component fatigue, mostly the steps and the step chain. A result that we weren't expecting is that it, poor lubrication doesn't impact the link tension, the step chain link tension. So now let's talk about the step weight and design. So it does impact the dynamic of the system, but no direct evidence was shown that it impacts the risk of collision, which is probably due to the problem I exposed earlier, the way we assessed their impact on the risk of collision. A result that we weren't expecting either is that it doesn't impact the torque required to operate the system. So the tensioning station adjustment, if we look at the table, the only impact it has is on the chain guide fatigue, which is quite a real result. The reason for this is that during our design of experiments, the values that were set to this parameter are fitted the manufacturer's requirements. So we had to run extra experiments where this time the tensioning station was incorrectly adjusted. And these experiments tend to show that it is the most non-environmental parameter, impactful parameter of the study. And finally, the lubrication of the tracks doesn't have any impact on any of the outputs. So, as I said in the introduction, the whole purpose of the study was to use the conclusion of this work to draw perspectives on our maintenance policies and design methods. So the first thing we did was to adapt our range of maintenance operations and our maintenance plan to the passenger flow. We also optimized our verification procedure of the tensioning station and step chain lubrication. We installed or readjusted safety rails to prevent any step rising. And finally, we are now taking into account the passenger flow more precisely into our calls for tenders. Because so far, we have only installed heavy-duty escalators, which makes a lot of sense for escalators located in the center of Paris. But for the escalators located in their underground, in the surroundings, they are clearly oversized. And for those who are wondering, a year after we started taking these actions, the number of pileups of steps has decreased by 60%. So thank you for your attention.